Hi, my name is Raghav Malik, and I'm a second-year PhD student studying with Professor Kulkarni. Today, I'm going to talk about the secure evaluation of vectorized random forests. In a data-driven world filled with concerns about privacy, there's a growing need for secure multi-party machine learning systems. In other words, systems in which the owners of the model, input data, and computational resources are different parties. Applications of this technology include banks sharing financial data while complying with regulations, hospitals sharing patient data while adhering to HIPAA, and users offloading sensitive computation to cloud providers. Of the many approaches to classifying encrypted features using an encrypted model, fully homomorphic encryption, or FHE, is a popular one thanks to its generality. Fully homomorphic encryption is an asymmetric cryptosystem that allows for homomorphically adding and multiplying encrypted ciphertexts without having to decrypt them first. In other words, if we carry out a sequence of operations consisting of homomorphic adds and multiplies over ciphertexts, the decrypted result will be the same as if we had carried out the exact same operations over plaintext. Since addition and multiplication comprise a universal set of gates, we can directly encode every one-shot arithmetic or Boolean circuit, including that of model inference, into a secure computation. However, we still have a problem. The homomorphic operations used by FHE are orders of magnitude slower than their plaintext counterparts, so this direct translation results in a computation that's far too slow to be of any practical use. Fortunately, this can be mitigated somewhat by a technique known as ciphertext packing. With ciphertext packing, we can encrypt an entire vector of plaintext values into a single ciphertext, such that any additions and multiplications we perform are carried out element-wise over the plaintext vector. In other words, we can treat FHE as a SIMD architecture and compile our models into instructions that target this architecture to execute them securely. Much of the recent work in this space has been focused on securely evaluating neural networks. This is an attractive choice because the computations involved in neural network inference are already vectorized. In certain cases, though, especially when the data is categorical, random forest models are better suited to the classification problem. Unfortunately, random forests present much more of a challenge to vectorize. The traditional algorithm for evaluating decision trees is to start at the root and walk down the path corresponding to the sequence of decisions until reaching a leaf. The control flow dependence between the current node and the next node to evaluate makes this an inherently sequential process that cannot be easily vectorized. There is some relevant previous research in this area, as listed here. The SIMD parallelization paper discusses techniques for parallelizing the evaluation of irregular data structures, including decision trees. However, these vector techniques require efficient random indexing into a block of contiguous memory, which is very difficult to do in constant time in an FHE setting. Chet is a compiler designed for homomorphic tensor programs, such as those of neural network inference. Although it has incredible performance with regular data structures like tensors, it is not built to deal with the fundamentally irregular programs we see in random forests. Finally, the blindfolded evaluation and classification of encrypted data papers both address performing secure inference over random forest models. The main technique used in these papers is encoding each bit in the classification result as a polynomial over the decisions. While this allows for packing polynomials for the same bit into SIMD slots, decision results are still evaluated sequentially, so the speedup is limited. Surprisingly, preventing timing side channel attacks gives us an opportunity to do better. A timing side channel attack occurs when an attacker can determine some information about the path taken through the tree by measuring the execution time. If one branch of a decision node is much deeper than the other, sequential evaluation will take much longer if it follows that branch. By measuring the amount of time a classification result is produced, the attacker can determine whether the longer or shorter path was taken. To prevent this kind of attack, we need to evaluate every node of the tree no matter what. Since doing so breaks the control flow dependencies between nodes and their ancestors, we are now free to rearrange the computation in order to make it more vectorizable. We propose a four-step protocol to efficiently classify encrypted feature vectors with a restructured model, as well as a compiler, Sever, which takes a random forest model and compiles it to the primitives necessary to execute this protocol. First of all, the comparisons are performed. The compiler constructs a vector of all decision thresholds, padded to give each feature the same multiplicity. We reveal the maximum multiplicity of the features to the data owner. They replicate their feature vector appropriately, encrypt it, and send it to the server. The replicated feature vector is compared to the padded threshold vector, yielding a Boolean decision vector that's padded with dummy decision results. The second step uses a reshuffling matrix primitive that associates each branch position in the tree to its corresponding location in the threshold vector. Multiplying the padded decision result vector with this matrix yields a Boolean vector with decision results ordered according to the canonical branch order. For each depth level of the model, we evaluate the result of the decision nodes at that depth, since there are no control flow dependencies between them. Each level has a level matrix and a mask vector. The matrix associates every label with the branch upstream from it at that depth, and the vector describes whether every label is on the true or false path of its upstream branch. Each level is processed individually. The level matrix picks out the decisions at that level which account for all the leaves. These decision results are added to the mask, giving a vector which describes for every leaf whether it is excluded or not by the decision result. Here, we see an example at a depth of 1. The decision nodes D2, D3, and D4 are selected to cover all the labels. L0, L2, and L4 end up on the false path, whereas L1, L3, and L5 end up on the true path, which is reflected on the mask on the right. At depth 2, we instead pick decision nodes D1 and D4, which puts L0, L1, and L4 on the false path, and L2, L3, and L5 on the true path. Finally, we can accumulate all the levels by multiplying these vectors together so that a label is only returned if none of the depth levels exclude it. This basically creates a vector containing the evaluation of the Boolean polynomial for each leaf. The vector can then be sent back to the client, who decrypts it and learns the classification result. We evaluated Sever on synthetic microbenchmarks as well as some real-world models. On the synthetic microbenchmarks, we found that when varying the depth, the time taken in comparison and reshuffling stages was unaffected, but the total time to process all the levels scaled approximately linearly, which makes sense since each level takes about the same amount of time. When varying the total number of branches in the model, once again the comparison time was unaffected, but the reshuffling and level processing stages scaled linearly. This is because without any parallelism, the time taken to do a vector matrix multiplication is proportional to the number of columns in the matrix. We also used 2 open source datasets to train models with a maximum depth of 5 and with 5-tree as well as 15-tree versions. We compiled these models and ran several inference queries on them in single-threaded as well as multi-threaded environments. Our results compare very favorably to the state-of-the-art presented in the blindfolded evaluation paper. Our smallest models had between 2 and 3 times as many decisions, but Sever was able to execute queries in less than half the time running in single-threaded mode. Multi-threaded on 8 cores, Sever executed queries on a model 7 times larger than its counterpart in comparable time. When compiled for a computer with 24 cores, Sever executed the same models 3 times faster, demonstrating its ability to take advantage of more parallelism. In conclusion, in this talk, I presented Sever, a vectorizing compiler for secure random forest models. On synthetic microbenchmarks, we see that while execution time is asymptotically linear in model size, Sever reduces some of the work by batching all decision node comparisons in a model into a single fixed cost sequence of vector operations. Sever is able to compile large random forest models into secure vector operations and execute inference queries on these models several times faster than the current state of the art. Furthermore, we see that Sever can also take advantage of a great degree of parallelism from multithreading, allowing it to scale more effectively to even larger models.